Okay, so the last day of the conference. I hope you have been enjoying the conference. This is the full paper session, Visual Analytics for Health Data. My name is Chol Kwan, go by BC. We have really exciting talks prepared for today, 6 exciting talks, which include 2 honorable mentions. So let us start our session with Claudio Linhers. Can you come up to the stage? So Claudio is going to talk about Clinical Path, a visualization tool to improve the evaluation of electronic health records in clinical decision making. Please ask your questions using Slido, as you did. Thank you.
Hello. Hello, everyone. My name is Claudio Linhares, and I'm going to present today our work at called Clinical Path, a visualization tool to improve the evaluation of electronic health records in clinical decision-making. First, I'd like to introduce about the physician's daily procedure. For physicians, analyzing piles of sheets and using systems with little visualization support is daunting, but that is still the usual way for physicians, especially in developing countries. Electronic health records, EHR systems, were designed to keep the patient history and to reduce the time analyzing patient data. About the EHR system, they can be improved by information visualization techniques. Recent surveys identify that they can be divided into population-based tools and single-patient tools. Population-based tools focus on general behaviors of simultaneously visualize the patient records. Popular tools include Lifelines tool and visitors. However, population-based tools are not meant for individual diagnosis hypothesis or patient clinical analysis. On the other hand, single-patient tools focus on local behaviors of visualizing a patient record, such as comparing test results and understanding their variation over time. Popular tools include MIVA, Carvis, and Visual Explorer. However, most of single-patient tools lack visual scalability, with visualization that require a lot of screen space to be displayed. Also, some of them lack interactive steps, such as grouping and filtering techniques. At last, some of them also lack evaluation with domain specialists, especially to understand the usability and usefulness. So we illustrate a regular clinical workflow, where the physicians perform a medical consultation. First, the physicians collect key patient data, such as age and sex, and determine the purpose of the visit. Then, the physicians analyze previous medical records and check the described conditions. Then, the physicians check the patient's medical history, such as previous surgeries, and performs a physical examination. In the decision-making phase, the physician can create a hypothesis in order to prepare an immediate plan of care, and additionally conduct tests to confirm or to discard the hypothesis. If the physicians feel comfortable, he can provide the diagnosis and start the treatment of the patient. Note that in the phase of analyzing medical records and to prepare individual plan of care, our system, called Clinical Path, also plays a crucial role in order to assist in choose appropriate dose of medications or to recommend procedures. So we propose Clinical Path, but first I will present the data set used in our experiments. We use a COVID data set, which is composed of 5 major healthcare institutions in Brazil. Together, they collect almost 600,000 patients and more than 32 million laboratory results. The current version of Clinical Path contains 9 selected patients, which presented interesting cases. So I will show now a demonstration of the system in order to show the functionalities and a use study. So here we can see in the first line the patient metadata information and also the general information about each day. Moreover, we have the categories. So for example, the red series hemogram category, which contains the tests, for example, RBC, HB, HCT, and RDW. Note that by just simply position the mouse in the top of the left circle, you have more information such as the complete name and the corresponding category of that test. The test results were divided into symbols, such as very low, low, normal, high, and very high. A participant mentioned that it was easy to learn the patient's condition using the symbols instead of values. So the system also allows us to change the colors. For example, we can just click select and choose a new color for that test. Moreover, you can select on a test and see the evolution throughout time. Note that in each column, there are different dates. So the information you have here, for example, the result, the reference value, and the change, which indicate how much that value increase or decrease when compared with the last timestamp. So for example, we have a result of 8.5, which is between 30.5 and 70.5. And this result is increased in 34%. So we have a result of 11.4. Also, more related to the changes, we can see that we added an orange border in the cases to highlight the cases where the changes was above 100%. Note that we also added this information at the top of the layout. So we can see the orange circles in the top to highlight the significant changes. About that, a participant mentioned that clinical path uses colors and patterns that allow quick decision-making. Also, the sims allows us to zoom out and zoom in using the mouse wheel in order to see a better overview. The system also allows us to double-click on a node and see a line chart that summarizes the complete result over time. Or we can select more tests, accumulate them into a single line chart. If we prefer, we can open those three selected ones into single line charts in order to compare them. The system also has the information of dates, which colors that represent blue for outpatient care, green for external service, and so on. This information is also available in the tooltip of the date. So now, I will present a case study where we focus on an exploratory analysis of a patient. Note that this is an elderly patient that is in a critically ill condition, based on the amount of tests at each day. By looking at the first three tests of this patient, we can see that they presented a lot of very low values for several consecutive days. This can represent malnutrition or even kidney and liver disease. To confirm that, we will look at the categories of kidney and liver. And we can confirm that by seeing that there is a lot of altered results over time. Moreover, by looking at a single exam, APTT, we can see that at some point occurs an abrupt change, which probably indicates a critical conditions where the physicians needed to interfere. So to validate our system, we performed a user study in order to understand if the physician could perform the diagnosed tasks. So we recruited 15 participants, all medical graduates in Brazil. The participants had to interact with the system in order to analyze the patient data. We applied to them a questionnaire where we asked about their background and experience and asked questions that required or not required medical knowledge. Overall, we achieved a satisfactory value of more than 90% corrected answers when the participants were using the system. We also asked them about their user preferences and collected their feedback. In that sense, we asked them about the intuitiveness and usability, the efficiency to optimize their time, if the system were easy to use, and the ease of system learning. Note that by looking at the blue bars as a positive values, we achieve a satisfactory value of more than 83%. So as we could see, clinical path plays a crucial role in helping physicians to perform diagnosis tasks. However, the system has some limitations and directions for future improvement. such as we could integrate clinical path with other similarized systems. We could include image data, such as X-ray, resonance, and tomography tests. We could also improve the visualization and interaction features, such as suggested by the participants in the user test. At last, we could adapt our system to a population-based tool. Here is my email for further contact and a QR code where you can find more information about the paper and the system. That's all. Thank you.
Thank you so much. All right, we have time for maybe a couple of questions. One question from Anonymous. Can physicians from different specialties reorder and group the exams according to their needs?
So probably talking about these categories, right? So for example, this ordering here is focused on general physicians. But let's say a physician from a specialty, we could choose this order of those tests. So in order to help them, to facilitate the visualization for them.
All right, so the next question I have is, would it be appropriate for physicians to share these visualizations with the patient, or are these mostly intended for just the physician to view?
That's actually a good question.
And how much training is needed to interpret these for you?
Yeah, I believe that this could be shared with the client, I mean. But I don't see a problem in that. That's the only problem I see that they will have trouble to understand what's going on. But yeah, that could be shared with the participants, yes.
All right, thank you so much. Let's thank the speaker once again. Let's move on to the next talk. Jillian Milozelev, which is a pre-recorded presentation this time. Visual assistance in development and validation of Bayesian networks for clinical decision support.
Hello, my name is Juliane Müller-Silav, and I'm very happy to welcome you to my talk about our visual assistance in development and validation of Bayesian networks for clinical decision support. So let's start. The common development process of clinical decision support models based on Bayesian networks requires medical researchers such as Hani and Stefanie providing the domain expertise and a modeling expert like Peter developing the model. This collaborative but generally time-expensive procedure, however, hampers in model generation and updating. Furthermore, because the modeling expert might make design decisions on the expert's domain, at some stage the medical expert may be confronted with a lack of understanding of the resulting Bayesian network model. To address these problems, we gathered the requirements on a visual approach allowing medical researchers to generate and validate clinical decision support models based on Bayesian networks mainly independently, and thus without the help of an additional modeling expert. But before entering our design requirements and visual approach, let's repeat the basics of Bayesian networks and their development. Briefly explained, Bayesian networks are probabilistic directed acyclic graphical models that represent probabilistic relations. For example, an effect represented by the node tumor recurrence is dependent on the causes of lymph node metastasis and therapy. A conditional probability table per node constitutes its if-then relations on parent nodes, where each node takes on a probability distribution. According to Subko et al., the common process of Bayesian network development and validation starts with data review and structural development, followed by structural validation, parametrization development in the form of conditional probability tables, parametrization validation, and model validation. We are taking this common process in our design and interaction requirements into account. Additionally, our tool is especially designed for a target audience of single medical researchers. But due to the complexity of the topic itself, an application within clinical routine is not intended. In summary, we identified the following main requirements. To reduce the complexity of the development and validation of Bayesian networks in our approach, we combine the parameterization development, parameterization validation, and model validation steps to the model parameterization and validation step. Furthermore, data review is necessary to assess the dataset's representativeness. Next, we need to explain the relationship between the causal flow among the information entities and the common practice within clinical routine. For this, we integrate the novel concept of clinical workflow steps groups. Additionally, data recorded within clinical routine allows for automatic model generation using learning algorithms. And within medical research routine, experts commonly use real patient data to gather new insights and validate guidelines. This familiar process should be adopted in our approach as well. Furthermore, there must be a balance between the required and optional development and validation steps. And last but not least, the tool should be usable without background knowledge in Bayesian networks. Now we want to explain and justify our interactive visual approach. We realized our front end as a 3-page layout according to our simplified steps in Bayesian network development and validation pipeline. Our approach starts with either uploading the data for data-driven development or selecting a version to rewrite. After loading a dataset related to endometrial cancer patients, we investigate the variable's quality based on distribution and missingness in the variable's small multiple presentation. Automatically, the best model structure based on this data is given below. For this, we compare the Bayesian information criteria of the potential network candidate scores generated using 6 widely applied learning algorithms and only present the best structure. In agreement with our collaborators, we decided to not present the mentioned score to the user to avoid confusion. This is a valid procedure since we integrate a user validation step in our approach later on. Here, the causal flow within the model is represented from left to right, which means from causes to effects, and the reliability of relations is encoded by edge thickness. Inspired by Xi et al., we apply cross-layer minimization to minimize edge crossings and present the nodes in topological order. Thus, not all edges are presented in static visualization, but are visible through hovering methods. We integrate the novel concept of clinical workflow steps groups in top to bottom order to help medical researchers in assessing the clinical pipeline and causal flow. Interactively, we can select variables for each reorderable group and integrate prior knowledge for model learning, for example. Next, we validate the structure for correctness. Individual subgraphs having no relationship to each other are emphasized through colors. This reveals, for example, the missing but already validated relationship from therapy to survival for 1 year, which we add directly in the network view. To validate all relations, an overview of the individual subgraphs is given below, and we present all relations in a list-inspired view with radio buttons for validation, with potentially related nodes emphasized having a dashed line. Furthermore, we can integrate comments and related clinical guidelines in the comments view below for later justification. When having a sufficient structure, the parameterization of the model is learned based on the dataset and needs to be validated. Inspired by common practice, we use real patient data for parameterization validation by representing the percentage of discrepancies between computed recommendation and given information in tones of red. Those differences are either reasoned on biases within the data or bugs within the model. By investigating the difference for a specific variable, we can compare the recommendation with the given information and investigate the key information leading to the recommendation. Then we can modify the parameterization for a given set of patient-specific information entities or modify the structure in case of missing impacts. When having a sufficient structure and parameterization, we can download the model and use it within clinical routine, for example. In our evaluation study, we focus on the assessment of the user experience and comprehensibility to identify potential weaknesses and improvements. This is essential before asking medical researchers to perform the very time-consuming process of developing a clinical decision support model. In doing so, we performed a one-on-one expert review evaluation study with 6 experienced gynecologists. Each evaluation study took approximately 1 hour, beginning with a short introduction and a brief overview of the tool. To make themselves familiar, we asked the participants to perform tasks to develop a fictional Bayesian network. Afterwards, they answered a questionnaire consisting of 35 questions. The participants assessed our visual approach as very useful in developing and validating clinical decision support models based on Bayesian networks. The users especially emphasized the integration of the clinical workflow step and the abstracted modeling steps as very good. To use our approach within medical research, however, we identified that the collaborative development needs to be supported. In the end, I want to conclude my talk and name potential future work. In summary, we presented an interactive visual tool that assists single medical researchers, such as Hani or Stephanie, in developing and validating clinical decision support models based on Bayesian networks. The tool can be seen as an intermediate step towards a collaborative construction of Bayesian networks. Our approach considers the workflow within clinical routine, as well as an abstracted and shortened pipeline in Bayesian network generation adjusted to medical researchers' needs. In an evaluation study with 6 experienced medical researchers with a domain-specific background in endometrial cancer, we assessed the usefulness and medical relevance of our approach as very useful. Potential future work includes the development of a tool for collaborative Bayesian network construction, as well as a long-time evaluation study with multiple medical researchers developing a real clinical decision support model.
All right, thank you so much. Let's thank the speaker once again. All right, so we don't have a question yet on Slido, but I have a question. Can you hear us?
Yes.
All right, so one question I have is, so did the concept of clinical workflow, the steps and groups, did it really help users understand this Bayesian reasoning in Bayesian networks?
Yes, it did. By showing both the clinical workflow steps and causal reasoning, our evaluation study participants understood that, for example, in causal reasoning, the tumor needs to be present to be visible in biomedical imaging. That means the tumor itself is a cause of the tumor presence in the MR image, for example, whereas in clinical workflow, medical images are often used to identify tumors.
Awesome. Another question from the audience. How statistically literate were the experts you worked with? And how did it impact the user study, you think?
What do you mean with statistical?
Did they understand all the statistics, like Bayesian networks? How much knowledge did they have?
Okay, like one was very familiar, I think, and most of them weren't familiar at all with Bayesian networks. And I think it depends a little bit, like on the how they used our tool, but mostly the most impact, I think, in my opinion, was the technical experience with computers. For example, we had one participant who was a little bit like not so familiar with technical stuff like computers also, and for him it was very complicated, of course, but one of our participants was very familiar with like computers and so on, and he was like, oh my gosh, I want to use it, and I think it's very nice and very helpful, and he was really into it.
Nice. Thank you so much, Julian. Let's thank the speaker once again. Now we're going to move on to the next talk of the session by Nicole Saltnam. And this work titled Chart Walk, Navigating Large Collection of Text Notes in Electronic Health Records for Clinical Chart Review. This work was recognized by the honorable mention. So let's give a round of applause once again for Nicole. And all the co-authors, please come up to the stage after the session so you can collect the awards, and then we have a photo session. So Nicole, whenever you're ready. And please ask your questions using Slido.
It's a little off. Let me try this again. Perfect. All right. Good morning. My name is Nicole Saltnam, and on behalf of my co-authors, I will present our journey with ChartWalk. Before seeing a patient for the first time, healthcare workers may do a study of the patient record to get acquainted with their health status and concerns, as you've probably seen in the first talk. Thank you. The patient record is a very heterogeneous data set containing notes, lab values, forms, imaging, and so on. That said, the parts that tend to be reviewed first are the text portions of the record, like the summary notes, diagnostic reports, progress notes. They're go-to sources because they're really information dense, helping get a quick but also fairly comprehensive overview of the patient. Sadly though, the more accurate take on text in medical practice is less like this and more like this, in that it's too much all at once. And it's something that puts a lot of time pressure on physicians who can't read this much in detail, with notes that are hardly standardized and hard to skim, with information scattered across many notes, and a lot of repetitive content across these notes. To help with that, past work in clinical text visualization tried to address this with visual summaries of record notes. And they're really helpful for content overview, but these heavily graphical approaches bear some core disadvantages when compared to text. First, they don't have the same communication bandwidth for details and nuance. And at scale, they are limited to semantic features that are feasible to automatically extract from text. And the use of automation, in turn, leads to trust issues, given that it's error-prone and stakes are really high for missing something important in a medical setting. So in summary, data visualization is powerful, but it's not a perfect substitute to text. That said, given the complementary nature of their pros and cons, there is value in assessing how to properly balance the two. So in this work, we advocate for a more hybrid design approach, or graphics plus text approach, very original, to strike a balance between the use of visuals and text in order to leverage the best of both worlds. And this approach has actually been on a long journey for us that started back in 2018 with MedStory. This was published at CHI, and it was when we first pushed for this graphics and text approach in medicine, with a small-scale prototype that mixed graphical elements and text in different ways, as you can see here. But it only supported a small number of notes at a time. After that, as follow-up work, we published Docurate, another clinical graphics plus text solution supporting much larger patient records. That said, the focus here was more on customizing information retrieval and dealing with automation, and less on getting an overview of the patient record per se. As such, in this work, we shifted back to the task of content overview, now at scale, with ChartWalk. We followed an iterative design strategy that included 2 cycles of design and evaluation, plus a set of formative interviews that collectively gathered feedback from 19 healthcare workers in mental health and critical care, some of which participated in multiple rounds. So I'll briefly walk you through this latest journey that begins from visualization design requirements we collected in our previous work including providing means to get an overall picture of the record, temporal awareness of the events in the medical history, means to rearrange content around particular facets or perspectives of the data, and to provide extensive access and shortcuts to the original text. Since these requirements were derived from studies with general practitioners, we talked with folks in mental health, a very text-heavy medical specialty, and asked about documentation-related challenges around their practice. More details in the paper, but we basically confirmed that our design requirements still hold for this practice. And so we created a first version of Chatwalk as a minimal viable product to fulfill those design requirements at scale. And it features a mentions view on the left to provide good starting points to the exploration. And it features a 2-level hierarchical list of occurring mentions organized under type, and then by body system and by issue, an organization scheme that was again informed by past work. For a second level overview, a curated snippets view contains text highlights with select information for notes that provides a bit more detail and context than just a list of terms. There's also a modified calendar view with the rows for months and markers for days featuring notes that helps convey temporal patterns. See there, for example, that there's a clear uptake on the number of notes in recent months, which is not a good sign. So to learn more, we can locate a discharge summary to read more closely, which are the orange markers that you see here. And after skimming that discharge summary a bit, we may want to make some more pointed investigations on symptoms. So back to the left, clicking on a mention replaces the curated view with a search view, and the calendar view also updates to show when the search term was mentioned, so temporal patterns are still visible. Direct searches can also be used to locate things on the overview panel or to search for completely new terms. So to evaluate this design, we recruited 11 healthcare workers for quick feedback sessions. And among actionable findings, we found that many participants found the mentions view valuable for overview, but some found it overwhelming, so expanded with better navigability. And also some temporal awareness was missing to discern which mentions were current and active issues versus historical ones. And so the mentions view on the left was expanded with more categories and better compartmentalization between each. And each mention was augmented with a spike line showing frequency of terms over time and indicates which issues may still be current. Third, some participants found that the system was still very note-heavy, which points to a need to make snippets and notes a bit less daunting and more visually organized. The snippets view was redesigned with a new organization level for episodes of care, which are basically intervals of hospitalization. And the calendar view was also updated to show episodes of care, which are the gray strips that you see under the day and note markers. And the notes view now has bolded headers that are automatically detected to help skim notes faster. Fourth, participants wanted to discern other note types beyond discharge summaries and suggested using color for that. So the calendar day markers are now colored based on the note types that they include, as conveyed by the legend that was added on top. A bar chart to the right of the calendar view shows the number of notes of each type on that month, and that helps better convey note density. The calendar view can be also sorted reverse chronologically, and content can be filtered out of the calendar and snippets view by toggling note labels on the legend, and that helps locate certain note types a little easier. And finally, participants were very positive about the idea of selecting snippets of their own to revisit later and to share with others, so we figured this was a good thing to offer moving forward. So content can be curated directly from text. The yellow segments are curated highlights, which show up in this dedicated highlights panel under the snippets view and are basically pre-segmented sentences in text notes that can be toggled on and off. We evaluated the second version of Chartwalk with the help of 5 healthcare professionals, where apart from their feedback, we also looked more closely at how the tool changed their workflows. What we found was a very diverse set of workflows, as showcased by the variety in usage patterns that you see here. That said, they all started the same way, by reading the latest discharge summary. So while not always a complete picture of the patient, it's often a good initial one that can be then complemented by the overview and the search features in the tool. Now, even those who use the overview features a lot said that it was really important that the whole overview to details spectrum was supported and that transitioning between these levels was easy. In addition, participants continue to be very positive about curation as a time-saving strategy via past highlights, but also as a support to their ongoing study. That said, we anticipate some issues could arise in the long run when we consider levels of sharing in collaborative spaces, and usefulness of highlights over time, which would need further investigation. And finally, participants appreciated the formatting with the bold headers, which leads us to consider ways that skimming can be better supported via other typographic features, more navigation aids, and so on. So what have we learned and where do we go next? First, and especially after the keynote this week, we can probably agree that reading isn't going anywhere. Text has awesome properties, healthcare folks are trained on it, and we should be leveraging these powers. Second, we underscore the value of curation and argue it could serve as a really nice placeholder to automation and as a metaphor for extractive summarizers to be seamlessly introduced into their workflows while facing less resistance from users, probably. And third, we argue that tools like ours that make lookup easier could have a very positive effect toward reducing note redundancy, since important details from past history could be more easily retrieved without having to repeat it again in later notes. For more takeaways and future work, please check our paper. And you can try the tool at chartwalk.cs.toronto.edu. Happy to take your questions.
All right. Okay, let me ask you a question. So you had 5 professionals and you talked about 2 mental health professionals. Could you also share some comments, observations you made about, generally about the critical care professionals in your evaluation or mental health professionals that you find interesting?
Could you repeat the question? Maybe closer to the microphone, I could barely hear
Oh,
it.
sorry. So what was the role of critical care participants, the professionals in your user study?
Oh, right, because I didn't quite mention that. So the mental health and the critical care folks were partly convenient sample. It's quite hard to do studies like this without having an ongoing relationship. That said, both the mental health and the critical care folks had very extreme requirements for text per user in medical practice. On one hand, as I already said, mental health folks have a lot of text to read. Their notes are quite extensive and very qualitative. But the critical care folks are constantly under time pressure, extreme time pressure. So we are talking about looking at several patients in an ICU and having only like 3 to 5 minutes to review these very, very complex patients. So they were both ideal people to talk to in terms of requirements for text.
All right. So in the interest of time, let's move on to the next talk. Thank you so much. All right. So next talk is going to be given by Eric Rido. The title of the talk is Development and Evaluation of 2 Approaches of Visual Sensitivity Analysis to Support Epidemiological Modeling.
Thank you for the introduction. Yes, my name is Eric Ridov, and I will present our work where we explore that visualization can be used to better support sensitivity analysis of epidemiological models. The context behind this work is that during the COVID-19 pandemic, models were rapidly developed and iterated upon as new information about the virus emerged. And this graph shows when, during the first wave of the pandemic in the UK, major model developments occurred. Modelers are interested in how the input or parameters to their models affect the outputs. This study of how inputs affect outputs is called sensitivity analysis. There are algorithms to help with sensitivity analysis. However, we found that they generally do not provide enough actionable information on their own for modelers to perform sensitivity analysis effectively. So we therefore worked with domain experts to develop two visual approaches to support sensitivity analysis. To make the discussion on COVID models a bit more concrete, the black curve shows the daily deaths during the first wave of the pandemic in the UK. All the blue curves correspond to different model predictions given different parameters for the same time period. As you can see, for some parameters, the model predictions match the real world quite well, but for many it does not. So the question then is, for what parameters does my model match the real world? Since if you find these parameters, you can use your model for forecasting, for example. Modelers are also interested in how varying different parameters changes the shape of the output time series. All of this can be summarized as sensitivity analysis. Sensitivity analysis is the study of how variations in the input to a model cause variations in the output. Why is this important? It's important as if you discover parameters which have very limited effect on the output from a model, you can probably remove those and simplify your model. It's also important if you want to tune your model parameters so the output matches the real world. Another important reason to do this is that if you find parameters to be important or not important in your model, they might also be important or not important for the phenomena being modeled. Commonly, this is done using algorithms at the moment. And what an algorithm takes as an input, in this case, is a scalar value. So for each output curve, you have to define a number to quantify what you're interested in about that output. So if you have a time series of daily deaths, you might be interested in the total deaths, as this is something you want to minimize. Once you've defined the scalar output, you then sample your model's parameter space uniformly, and you can arrange it, as shown here, with the value of the output on the y-axis and the value of the parameter on the x-axis. What algorithmic sensitivity analysis does is it gives you a number for how well the points end up on a line. So if it ends up on a line quite well, the model is considered sensitive to this parameter. If it doesn't, the model is considered less sensitive to this parameter. You can compute these numbers for all of the parameters in a model, and this is shown here in a simple model as a bar chart. And I'm showing this bar chart to get an idea of what sort of things you can see from algorithmic sensitivity analysis. You can see parameters which are not important, but of the parameters that have long bars that the model is sensitive to, it doesn't tell you how the model is sensitive to these parameters. So it doesn't tell you if I increase this parameter, does the deaths go up or down? It doesn't tell you in what range the parameters have what effect, since some parameters can have a certain effect in the lower part of the range, a different effect in the upper part. And also it only works with scalar features. So you might imagine, if you find a parameter to be unimportant for total deaths, you remove it from your model, it might actually have been important for like the height of the peak or some other scalar feature you're interested in. So modelers are very hesitant to modify their models based on just these indices. The way the workflow therefore works currently is that modelers first compute the indices, and based on this, they then look at individual model runs. And then they know which parameters to modify to see how the actual outputs change. The second part of studying individual model runs is very time consuming, and this sort of creates a bottleneck for the whole sensitivity analysis process. We therefore developed two visual approaches to address these problems. Our first approach we call algorithm-centric. The reason we call it algorithm-centric is that the inputs are the same as the inputs to the algorithm. So you perform the same analysis as you do for the algorithm up until a point where instead of presenting the result as a number, you present it as a small graph, therefore like conveying more information to the modeler. Our second approach we call visualization-centric, and here the idea is to try to visualize all the outputs as time series and what they correspond to in the input space. So if we start out with the algorithm-centric approach, at first it looks very similar to the analysis the algorithm does. You pick a scalar feature, sample parameter space uniformly, arrange it based on the value of a parameter. We then use a Gaussian process emulator, which is beyond the scope of this talk. But the neat thing about the Gaussian process emulator is that it allows us to estimate the average effect of varying just the parameter in question. This is shown as the red line. So in this plot, the red line shows that as the probability of infection is between 0 and 0.5, increasing it means deaths go up. Past about 0.5, it starts to have a different effect. And this is something that algorithmic sensitivity analysis alone with a single number doesn't convey. We can then repeat this for all the parameters to produce a grid like this. And from this, modelers were quickly able to identify from the gradient of the red lines which parameters were important, but also how they are important. Our second approach, visualization-centric sensitivity analysis, tries to visualize or tries to present all the output curves. The problem that the modelers faced previously is that reasoning about 200 curves, for example, is very difficult. Trying to reason about how, like, what combination of parameters makes this curve look different from another curve. So what we do instead is we use clustering to group the curves into a limited number of clusters. So then you can reason about what makes curves end up in this cluster and not this other cluster. So you only have to reason about, in this case, 4 clusters instead of 200 curves. The question then is, how do you show the input space along with this? Since just showing the output space doesn't give you any idea of the sensitivities in the model. Through discussion with epidemiologists and modeling scientists, what we came up with was a pixel-based approach, where for each cluster, we show a colored bar, where the color of the bar corresponds to the color the mean of the cluster is shown as, and the bar corresponds to the range a parameter takes in this cluster. On top of the range, we show the distribution in more detail by showing individual ticks, and these ticks correspond to parameter values for runs in this cluster. You can then repeat this for all the clusters and all the parameters to get this type of pixel-based overview. This may seem complicated at first, but when we showed this to modelers who had experience working with this model, they were quickly able to use this to reason. If you study this, you might see that the yellow cluster sometimes corresponds to having very few deaths or no outbreak. And if you look at the input space, you see it's the only cluster where the value of the parameter p_s is under half. So this quickly gives you an idea that actually this value is important. And when it's below a certain threshold, very few people tend to die. That's useful. We also showed this model to an epidemiologist who had experience working with the pandemic in Scotland. And what he was interested in is what separated the green cluster with the high initial peak of deaths from the red cluster, which on average has a later, lower peak of deaths. And by studying the input parameters for these clusters, they mostly overlap. But if you look at this parameter, which corresponds to the time between someone getting COVID and them being infectious to other people, this is on average greater in the red cluster. And this then tells you quite intuitively that if it takes more time between a person getting COVID and them infecting others, you will have a more flattened curve. However, this wasn't shown from the sensitivity indices alone. So we found this quite exciting. In summary, current algorithmic sensitivity analysis workflow has limitations, as it doesn't provide modelers with enough high-fidelity, actionable information on its own. We collaborated with a team of domain experts to address this, and through this collaboration, we developed 2 visual approaches to support sensitivity analysis. If you want more information about our approaches, please see our paper. Thank you.
Thank you so much. We don't have a question, Slido, but I do have. What do you think about the generalization of your approach to other types of models?
The algorithmic approach should generalize quite well, since if you have data which you can do algorithmic sensitivity analysis, you will be able to apply that approach to visualize it instead. The clustering is really dependent on what model you have, what outputs, if you can cluster the outputs nicely and show it nicely. So yeah, at least the algorithmic approach should generalize quite well. Yeah.
Okay. We do have another question. Is there a way to automatically point out key insights from the parameter values distribution to lower the cognitive load?
That's actually a very good idea. Yeah, there probably is, and we hadn't thought about that. Yeah, that's a good suggestion.
All right. All right, thank you so much. Let's thank the speaker once again. And we move to the next talk of the session. Mang Di Zhuang, It's a pre-recorded talk, a framework for evaluating dashboards in healthcare.
This is Mandy Zhang from the University of Sheffield, United Kingdom. Today I will introduce a joint work with Dave Concanen and Ab Manley, in which we developed a framework for evaluating data dashboards in the health sector. Healthcare presents a wide range and interesting use cases for data dashboards. In clinical decision-making, doctors use dashboards to view patients' health records and make recommendations to the patient about their treatment. Dashboards are also essential to support key administrative processes in hospitals and healthcare research institutions, such as managing drug stocks and available beds. In recent years, there are more and more individual-facing dashboards as self-management tools, such as organizing daily schedules to fit in treatment actions and promote healthy behavior. Dashboards are also being used in public communication about health risks, informing the public of potential threats, justifying decision-making and policy, providing evidence, assurance, and analysis to a variety of users. Our review, however, reveals that many use cases still don't have targeted evaluation procedures. We hypothesize that it is impossible for static evaluation frameworks to keep up with the ever-shifting base of user needs and associated use cases. Most often, it is only the evaluation of the intended task that makes its way into the design process, with sole focus on the interaction of the user during the performing of the task. However, in reality, the global use of dashboards impacts collective social and professional consciousness at a more subtle level. Outcomes that revolve around long-term changes in information acquiring patterns, decision-making, and health-related behavior are harder to measure with only a task-focused approach. In a rapidly changing field, where novel use cases and tasks are continuously being developed, such a classification covering wider impact is therefore advantageous. To operationalize our evaluation framework, we propose a new definition of data dashboards. This definition has the advantage of highlighting the corresponding components of a dashboard that will become the focus of evaluation. We say that a dashboard is a visual information system which comprises at least one visual figure and a store of data which the graphic user interface exposes, and which is designed and built with the purpose of fulfilling a precise information need. By visual figure, we refer to a visual medium of communicating data. It can include charts, icons, or visual cues. A dashboard's purpose is accessing and understanding data relevant for a concrete problem, and their means of achieving this purpose is inherently visual. Data is at the foundation of a dashboard. Its organization, representation, and dissemination is intrinsic to a dashboard's goal. As an information system, however, the dashboard falls back on standard system design constructs. The graphical user interface, which presents an interaction and information access channel to the user. The underlying task that the dashboard enables is not excluded from our analysis. Indeed, it is an intrinsic part of the dashboard's definition. In order for designers to guide the dashboard towards its purpose, a particular type of tasks or set of tasks is designed and engineered into a dashboard directly. Such tasks are developed in relation to context-driven problems that the dashboard is intended to tackle, and we refer to them as the dashboard's intended tasks. It is, however, important to recognize that, upon deployment in their respective ecosystems, evaluation by intended task quickly becomes stale for most dashboards. In our review and resulting framework, we find ourselves often placing emphasis on interactions that occur outside the dashboard's design scope due to the measurable real-life impact observed. This departure from evaluation according to intended design is a novelty in our framework and encourages a focus on the impact of dashboards not only on its intended user groups, but related sectors of the public or community indirectly. Our new evaluation framework contains 7 evaluation scenarios under the umbrella of 3 distinct themes. We take a systematic approach for describing the evaluation scenarios, focusing on aims and criteria and providing extensive examples from the literature of how to measure these outcomes in practice. We collect individual challenges for each scenario that system designer needs to be aware of and potentially aim to address as part of novel research. Furthermore, we exemplified our methods through constructing a dashboard design. In the following slides, we will briefly go through the framework we developed and describe the key evaluation scenarios. As promised, 3 major themes serve to organize our approach, namely interaction effectiveness, which measures how effective the dashboard is while the user interacts with it, focusing on how the interaction develops, the effects of interaction on a task, or in the long run between the user and the dashboard. The user experience focuses on users' subjective feedback in terms of usability issues, extra functionality to include, and the intent to engage with the system in the future. System efficacy relates to whether the system contains an accurate algorithm or has stable outcomes. We also care about the quality of the implementation of the dashboard. Usually, dashboard evaluation comprises of a multitude of these themes pre- or post-development. Moving on to each individual scenario, task performance is one of the most used scenarios, and also what we call the intended task evaluation. The aim here is to assess the effectiveness of the dashboard with respect to the performance of a particular task or tasks across multiple users. Behavior change assesses the dashboard's ability to induce positive long-term influences on users' behavior. Interaction workflow aims to assess how users interact with the dashboard from the point of view of information seeking, communication, and decision-making efficiency for the intended task and context. Perceived engagement assesses the subjective feedback collected directly or indirectly from users regarding their perception of the user experience. Potential utility assesses the dashboard's potential secondary tasks and supplementary functionality in addition to its current design or use. Algorithm performance assesses whether the algorithms embedded in the dashboard are correctly designed and return reliable information efficiently. System implementation assesses whether the implementation of the dashboard is appropriate for the user's work environment. For example, does it pay enough consideration to physical and hardware constraints? The 7 scenarios determine a cohesive method which can be used to conduct evaluation from all angles, covering both short-term and long-term outcomes, and most importantly, evaluating dashboards as an information system, not merely as a visualization. Critical novel methodology is described in more detail in our paper. Make sure to check out our extensive list of examples and the demonstration of our methods in our own case study.
All right, thank you so much for your talk, Wendy. Okay, one question to you. Can you hear us, Wendy?
Yeah,
So,
sounds good. Yeah.
yeah, you mentioned about the behavior change as one of the components. What are the good ways to evaluate behavior change? Can you share your idea or thoughts?
Yeah, of course. I think evaluating behavior change is quite tricky as it usually involves revisiting the users or including them into a longer term process. I think in the typical HCI field, quite a lot of researchers or designers have already done so. So, for example, revisit the users and to create mechanism for them to provide feedbacks in longer term. Yeah.
All right, great. Thanks for your answer. We have a suggestion. Would be interesting to link this framework to Mayer's and Munzner's 4-level nested model for visualization evaluation. Has that been done?
Sorry, I missed the suggestion.
So there's existing framework, Mayer's and Munzner's 4-level model. So,
yeah.
And did you link your work to that existing framework in your paper? If not, I think it's a good idea to do that. I think that's what this suggestion is about. Yeah.
Yeah, sure thing. I'm actually really a fan of that work. So this is a TVCG work, so a little bit longer content than I could put in the video. We discussed a little bit about the connections with that work, and they're really happy to discuss it further. Yeah.
All right. Thank you so much, Randy. All right. Let's thank the speaker once again. All right. So we have the last talk of the session. Chenwen Wang. The title of the talk is Extending the Nested Model for User-Centric XAI, a design study on GNN-based drug repurposing. This work was also recognized by honorable mentions, so let's give a round of applause to Chenwen. And I must say she's also on a job market, so if you have a job offer, please come talk to her. All right, Chenwen.
Thank you so much for the nice introduction. And yeah, now I'm officially the last paper talk of IEEE WIS 2022. Thanks so much for staying here with me. I promise you this is an interesting talk that is worth your time. And yeah, we were talking something about AI explanations. Yeah, and sorry, Nacho. I'm Jiwen Wang from Harvard Medical School. Today we are presenting Extending the Nested Model for User-Centric XAI, a design study on gene-based drug repurposing. Don't be scared away by the terms such as GNN and drug repurposing. I promise you this is a general audience-friendly talk. First of all, I would like to thank my fantastic collaborators and mentors. The Honorable Mention Award wouldn't be possible without their support. I first want to make a claim that this is not another XAI visualization tool. Such as a big claim, why? Let's first take a look at the existing AI visualization tools. So existing AI visualization tools are usually designed for one specific AI explanation, such as rule-based explanations, counterfactual-based explanations, and attribution-based explanations. Although stories are exciting as they are able to effectively present the hidden information in the black box. However, they're often designed and evaluated on general tasks, such as show me some explanations, it must be better than nothing. But when we design visualization tools for end users to solve the domain problems, it's very important to note that not all AI explanations are equally usable. Here are some examples. Attribution-based explanations explain a prediction by highlighting the most related regions in the input. However, studies showed that this widely used explanation technique cannot help users identify defective models. Counterfactual explanation describe which input change will lead to opposite model predictions. Even though this explanation is considered to resemble how humans make decisions, it does not improve calibrated trust compared with other explanations. The two finger examples that does not mean that the explanations are not usable. For example, where attribution-based explanations are criticized for the classification of nature images. It is actually a very useful technique in regulator genomics by identifying the related genomic locations and how people decode the genome functions. In other words, which explanations work or do not work is extremely data type and application domain specific. Therefore, when designing tools for domain users, we should not just visualize the results of a popular AI explanation, but consider the user's needs, the usage context, and the type of explanations all into the design process. Some recent studies have investigated the integration of XAI considerations into the user interface design. However, they are designed for general users and provide little discussion about visualization design. On the other hand, design visualization for domain-specific problem is a well-studied topic in the visualization community. Many design models and frameworks have been proposed. Can we apply those design models for visualizing AI explanations? Our answer is yes, and this is exactly what we did in this study. We incorporate a diverse set of user-centric XAI design considerations into the different layers of visualizing AI explanation, based on a literature review and our collaboration with domain experts. Specifically, we focus on graph neural networks in drug repurposing. The input data is a knowledge graph where nodes indicate medical entities such as drugs, disease, proteins, and edges represent the relations between those nodes. The gene model predicts whether an edge exists between a drug and a disease. That is, whether a drug can be used to treat a disease. Due to time limitation, I will only introduce several design considerations and how we incorporate them into our visualization tool. First, in the domain abstraction layer, we examine how a human expert would reason about a phenomenon, which is called domain explanation. In our case, we want to understand how medical experts would reason about a drug indication. And then, in the explanation abstraction layer, we investigate the format of AI explanations. Through a survey of current gene explanations, we identify three common visual presentations of gene explanation: graph-based, path-based, and node-based. By comparing them to how human experts reason about a drug indication, we identify that path-based explanations are more similar to the domain explanation. In terms of the granularity of explanations, users desire not only local explanation, that is, an individual path that explains a certain drug prediction, but also group explanations that can explain multiple similar drug predictions. We use MathPath as a group explanation, which consists of a sequence of node types and relation types. Putting all those design considerations together, we propose a math matrix design. Each column is a drug, and each row summarizing the explanations belonging to the same group. The cell indicates the number of individual passes, and users can click to further investigate the explanations within an explanation group. Okay. Here I present a brief use case of the proposed visualization tool. User first choose a disease of interest. Here we choose Alzheimer's disease. The embedding view shows the embedding of all drugs in the knowledge graph and highlights the predicted drugs. The MathPath view provides path-based explanation for all drug predictions. Similar drugs form a cluster in the embedding view. Here we choose one cluster, which consists of anti-diabetic drugs. The prediction of those drugs is consistent with the current understanding about diabetes and Alzheimer's. We choose one drug, Repaglide, in this cluster for detailed analysis. Users can expand or collapse, hide or unhide path explanations as needed. Here, Repaglide is predicted partially because this disease and Alzheimer's share the same protein. Another explanation of Repaglide is related to ibuprofen, a painkiller that shows benefits for treating Alzheimer's. We can also observe that similar drugs in the same cluster share some similar explanations. We further conducted a user study and expert interviews to evaluate this visualization tool and the design process. I only report some findings of this evaluation. Here, we can show that with path-based explanation, users are able to perform tasks more accurately, confidently, and quickly. Surprisingly, we also found that a poorly-based visual explanation, which is a node-based explanation in our case, is not necessarily better than non-explanation baseline. That is a very interesting observation. In summary, here are three main takeaways. First, not all AI explanations are equally usable for the end users, and we should keep that in mind when designing AI visualization tools. Second, we present a design process where we extend the nested model for user-centric AI, and we design a visualization tool based on this design process. We believe the observations and insights from the design process and the visualization tool can be generalized to many other domains. Now, this is the end of my presentation. Thank you so much. I'm happy to take questions.
Okay, so we don't have a question on Slido yet, but I do have one. What's your rationale behind choosing the tasks? So you mentioned about why, what else tasks?
Let me, oh. Yeah, I think when we choose the task, we actually also from a user-centric XI perspective, we basically identify 5 types of explanation operations that users usually conduct towards individual predictions. So, for example, here like why not, what if, how to, and what else. Why means like why a prediction is made, and why not means like why a certain prediction that the users believe are not made. And what if means how a certain change to the input will influence the prediction. How to means the adjustment needed to generate a different prediction. And finally, what else means the users want to query some similar instance that generates similar predictions. And so we're somehow using those explanation operations of the design space, and then we consider how the users will use those visual explanations in their usage context. And we finally define why and what else the main task that we want to help users achieve in the visualization tool.
Right. Yeah, thank you so much,
Yeah.
Shenwen. Okay, let's thank the speaker once again. All right, this is it. Thank you, all the speakers. Amazing talks. And thank you, audience. This was the last session of the conference, so please enjoy the last coffee break of the conference, and we're going to have capstone here and room number 4 too. And also co-authors of the papers who got recognized by the honorable mentions, please come up to the stage so we can give away the certificates and also have a photo session too. All right, thank you so much.